Good morning everyone. Today we'll be going through the output equation of a transformer in the first part, and the second part is the voltage per turn. We are going to look out for these two derivations. So in the beginning of the derivations, we'll get familiarized with the notations that we are using. Okay, so we have the phi m, that is a main flux in Webers. Then Bm, that's the maximum flux density, Weber per meter square. Delta, that is the current density, ampere per meter square. AGI, that is the gross core area, meter square. AI, that is the net core area in meter square, which can also be found out from gross core area by multiplying it with the stacking factor. Then we have the AC, that is the area of core copper in window in meter square, and AW, that is the window area in meter square. KW, the window space factor, which is a ratio which we will see in the derivation. Then F is the frequency in hertz. The next one is ET, that is the EMF per turn in voltage. Then we have TP and TS. They are nothing but the number of the turns in primary and secondary windings respectively. Then we have IP and IS, that is the current in primary and secondary winding respectively in ampere. Then we have the VP and VS, that is the terminal voltage of primary and secondary windings respectively in volt. And then at last we have small ap and small as, that is the area of conductors of primary and secondary windings respectively in meter square. Now we will go through the derivation. First we'll be starting with single phase transformer, right? So we know we have the basic equation, that is the voltage induced, okay, so which is actually 4.44 F phi m N1 or N2, depending on whether it is the E1, that is the primary induced voltage, or the secondary induced voltage. Okay, so with the help of that, okay, we are taking the equation for voltage per turn, that is ET, okay, which is equal to the induced voltage divided by number of turns, which is equal to 4.44 F phi m, right? So E is equal to 4.44 F phi m N, or the T, right? So that is being brought here, so that gets cancelled here. So that is why I have the volt per turn is E by T, which is equal to 4.44 F phi 1. We'll have this as equation 1. Okay, next, the window in single phase transformer. Okay, so in single phase transformer, it contains one primary and one secondary windings. Okay, that is what is the catch here, right? The window in single phase transformer contains one primary and one secondary winding. So we are going for total copper area in window of a single phase transformer. So that is denoted by AC, which is equal to copper area of the primary winding plus copper area of secondary winding. So we have the number of turns, primary turns, into area of primary conductor. So this will give us the copper area of the primary winding, that is number of turns into area of primary conductor, plus the secondary turns into area of secondary conductors. So this will give us the total copper area of secondary winding. So AC is equal to, as we have, right, so it is TP, okay, that is the number of turns in the primary, into AP, okay, that is the area of the primary conductors, right, plus TS, that is the secondary, and that is the number of turns, and we have the AS, that is the area of conductors in second. Okay, so this is the AC, that is the copper area in the window. Next, taking the current density delta to be same in both primary and secondary windings. Okay, so the basic equation for current density is current per meter square. Okay, so that is what we have. That is why it is ampere per meter square now, right? So we have AP, that is the area, which will be equal to IP by delta, right? So because delta is equal to current per AP. Okay, so current per area will give us delta, so we are calculating the AP from that equation. Okay, and similarly AS, that is the area of the conductor in secondary, is equal to IS by delta. Okay, so these two equations we have, that is a relationship between the area and the current density. Okay. Next, total conductor area in window, which was AC, that is, okay, so that was, right, we had was TP AP plus TS AS. Okay, so we'll have this as equation 2, these 3. Okay, so from equation 2 we have it is. Now what we are doing here is, in this we are substituting the value for AP and AS. Okay, that is what we'll be doing here. So it is equal to TP as it is. So AP is IP by delta plus TS. Okay, TS as it is, and AS is IS by delta. Okay, so when we simplify this, right, so we get TPIP, right, plus TSIS whole divided by delta. Okay, right, and right, so if you are taking TPIP and TSIS to be equal to 80, that is the amp turns, this is nothing but turns and ampere only, right? So we are taking TPIP equal to TSIS, right, which is equal to 80. So right, so to assume this, we'll have to neglect the magnetizing MMF. When we are neglecting the magnetizing MMF, we get this equation. So therefore AC will be equal to, so this will be 2 times 80 by delta. The next is the window space factor KW that we had already taken in the notations, right? So what it is defined as the ratio of copper area in winding to total area of the winding. Sorry, it is the window, right? It is window space factor is the ratio of copper area in window to the total area of the window. So KW will be equal to conductor area in window divided by total area of window. Okay, so which is AC by AW. Okay, so with this we can get the relationship for AC, which is equal to KW into AW. This is the equation we get for AC. Okay, so from the earlier equation, that is from this equation, we also know AC is equal to 280 by delta. Okay, that is what we will be making use here. So it is 2 times 80 divided by delta, which is equal to KW into AW. Therefore 80 will be equal to KW AW into delta, okay, whole divided by 2. Okay, this is the equation we have, kW AW delta by 2. Right, the next one we have is the kVA rating. Okay, that is the kVA rating of the single phase transformer Q. So Q will be equal to, right, Vp Ip, okay, into 10 raised to minus 3, because it is in kVA, kilo, that is why I have it. So this is all will be equal to Ep Ip into 10 raised to minus 3. Right, it is always, right, approximated that Vp is approximately equal excuse me, sorry, Vp equal to Ep. So that is what we are, right. So Ep is nothing but Et, that is volt per turn, okay, into turns. Okay, so with this it will get Ep, that is the per turn volts into number of turns, okay, into Ip. Alright, so into 10 raised to minus 3. Okay, so we will be substituting for this Tp into Ip. Okay, so that we have already taken. From this we have, right, so Tp, yeah, Tp Ip is equal to 80, that we will be substituting here. So it is Et into 80 into 10 raised to minus 3. Okay, next we will be substituting it for 80, right, so which we have the value for 80, right. So from this, right, so 80 is equal to kW AW delta by 2. So this will be equal to Q is equal to Et into kW AW delta by 2 into 10 raised to, so Q is equal to 80 into kW AW delta by 2 into 10 raised to minus 3. Okay, now we have the equation for Et. Okay, so this is what the equation for Et we have, 4.44 F 5m. Okay, that we will be substituting here. So it is 4.44 F 5m into kW AW delta by 2 into 10 raised to minus 3. So this and this, so it is 2. Okay, so we will be getting here 2.22 F 5m kW AW delta into 10 raised to minus 3. So this is Q. Okay, so one thing next we can do is equate the value for 5m. Okay, because 5m, right, so it is nothing but, right, so we have the basic equation, density is flux per area, right. So flux will be, or here just as a normal flux it is B into A, so that we will be substituting here. So Q will be equal to 2.22 F Bm, that is the maximum flux density, into AI, okay, that is the area, right, into kW AW delta into 10 raised to minus 3. Okay, so Q is equal to 2.22 F Bm AI, right, kW AW delta into 10 raised to minus 3 kVA. So this is the equation that we have for the kVA rating of a single phase transformer. On similar for single phase transformer, what we have done, similar will flow, that is the similar points will be there for calculating it for three phase transformer, right? So we should know what is the change, right? So the change here is, in case of three phase transformer, each window, right, contains two primary windings and two secondary windings. Okay, so whether if it was, when it was in a case of single phase, it was one each, that is one primary and one secondary winding in window, each window, right? But now it is two in three phase winding, right? So on similarly we'll go for AC, that is the copper area. Okay, that is a conductor area, right? So here it will be, right? So when we got to the first one, right? So when it was this much, right, TPAP plus TSAS, when it was one turn. Now we have, for three phase we are having two turns, so it will be 2 times, okay, TPAP plus TSAS. Okay, fine. On the similar basis, again we'll take it for current density, right, delta, right? So that will be equal to, substituting the value here, okay, it is 2 times IP TP by delta plus IS TS by delta, which is equal to 2 times, okay, IP TP plus IS TS divided by delta. Again, as per the earlier derivation, right? So when we take this, okay, that is TPIP is equal to TSIS is equal to AT, that we will be substituting here, right? So what would we get here is, that is 4 times, okay, 4 times AT by delta. This is nothing but, so this is nothing but AC. Okay, so earlier we had got was AC, for single phase we had got was this much, that is 280 by delta. Now for three phase we are getting it as 480 by delta because of two windings. Okay, so right, so next total again, right, the conductor area, right? So it will be, which is also, that is, right, 4 times AT by delta will be equal to KW AW, or AT is equal to KW AW delta whole divided by 4. Okay, so this is very much similar to our previous derivation, right? So where we had AT was equal to, right, you could see AT is KW AW delta by 2, right? Here it is by 4, right? Again with the same steps for three phase transformer. So Q will be equal to here 3 times VP IP. Okay, it is three phase transformer, so 3 times VP IP into 10 raised to minus 3, okay, which is equal to 3 EP IP into 10 raised to minus 3. Right, so which will be equal to 3 ET TP IP. Okay, so EP, right, that is the total voltage, right? It is given in terms of the volt per turn. So this is volt per turn into number of turns, okay, which we get. So this will be equal to, again, TPIP is substituted with AT. Okay, therefore we get 3 ET AT. Okay, into 10 raised to minus 3. Okay, so now again we'll substitute for AT with this value, so which will be equal to 3, right, into ET. ET is 4.44 F 5m. Okay, from the basic this equation. 3 into 4.44 Fm AT. AT is kW AW delta whole divided by 4 into 10 raised to minus 3. So this, so it turns out to be 3.33 kW AW delta into 10 raised to minus 3. Okay. F. Again substituting for flux with terms of flux density and area. Therefore Q is equal to 3.33 kW AW Vm into AI into 10 raised to minus 3 kVA. Okay, so 3.33 kW AW AI, right? Also frequency. Right, so the total final equation is 3.33, okay, F kW AW AI delta into 10 raised to minus 3. 3.33 F kW AW AI delta into Bm to 10 raised to minus 3 kVA. Okay, right, so these final equations that we have, okay, that is for single phase and three phase, right? So we had it for single phase. Here the equation A 2.22 F Bm AI kW AW delta into 10 raised to minus 3 kVA, and the one we are having for three phase 3.33 F Bm delta kW AW AI into 10 raised to minus 3 kVA. This is for three phase. These two equations, that is equation A and equation B, holds good for both core type and shell type of transformer. So in continuation, we will go for the second part, that is the output equation in terms of volt per turn. Okay, so here we will be taking for one phase. Okay, so we have, right, so it is Q, which is equal to IP Vp into 10 raised to minus 3, which is equal to IP into 4.44 F 5m TP, right, into 10 raised to minus 3, right. So this Q is equal to 4.44 F 5m right, TP TP into IP, which is ampere into 10 raised to S3 kV. Okay, next, right? Right, so now we are taking a ratio that is a constant K. The ratio phi m by ampere is a constant for a transformer for given type, service, and method of construction. Okay, so the type means what type of transformer it is, right? So service it would be for power or a distribution transformer, and method of construction, that is for a shell turn. So this ratio of phi m by amp turn is a constant, and it depends on these many parameters, these three, right? So we are taking phi m by AT to be equal to R, where R is a constant. Okay, right? So Q is equal to 4.44 phi m F AT into 10 raised to minus 3. Okay, the one which we have got here. Okay, so with this, right, so it is 4.44. Okay, Fm F phi m by R into 10 raised to minus 3. So what AT is been replaced with what? Phi m by R. So we can see here phi m by AT is equal to R. Okay, so AT will be phi m by R. That is what is being substituted here. Okay, therefore it is equal to 4.44 phi m square F by R into 10 raised to minus 3. From this, we are getting, from this equation, okay, we are getting the value for phi m, okay, which will be equal to square root of R into 10 raised to 3 divided by 4.44 into F, okay, into, so we have phi m, right? So when we substitute wins, we bring phi m square to one side, we get Q into R divided by F into 4.44, that is phi m square. So phi m will be square root of that. Okay, so that is what is being done here. Right. So next, voltage per turn ET, again from the basic equation, it is 4.44 F phi m. Okay, that is what we are writing here, right? So ET is equal to 4.44 F phi m. Okay, so now we are substituting the value of phi m. Okay, so this is the value that we have for phi m. Okay, so that value will be substituting. So it is 4.44 F into R into 10 raised to 3 divided by 4.44 F into Q whole raised to half, which is nothing but the square root that we had. Okay. So ET will be equal to square root of 4.44 F, okay, R into 10 raised to 3 into Q, right? So ET is equal to K into square root of Q, the kVA rating. Okay, where K is equal to square root of 4.44 FR into 10 raised to 3, or it is 4.44 F 5m by 80 into 10 raised to 3 to the power of half. Okay, so as we already decided or told earlier, the ratio of 5m by 80, it depends on type of transformer. Okay, so and the values for K for different types of transformer are in this table. Okay, so if you are having a single phase shell type of transformer, the value is between 1 to 1.2, the value of K. Single phase core transformer 0.75 to 0.85. Three phase shell transformer 1.3. Three phase core, that is distribution, okay, the service 0.45, and three phase core transformer, that is for power transformer, then we have it to be between 0.6 and 0.7. Okay, just to summarize the whole this, right? So we have for a single phase transformer, okay, the equation, output equation 2.22 F Bm delta Kw Aw Ai into 10 raised to minus 3 kVA, and for three phase transformer 3.33 F Bm delta Kw Aw Ai into 10 raised to minus 3 kVA, and the equation for volt per turn Et is equal to K into root of Q. Okay, so this is the these three equations. Okay, thank you.